So I'm Philipp Moesta. I'm a postdoc staff scientist at UC Berkeley, currently moving to the University of Amsterdam as a faculty member in September. And it's a pleasure to be back here in Sun River for the Blue Water Symposium. It's always great to be back here and see all the interesting and outstanding science that's being achieved and enabled by blue waters. Today I'm going to be talking about magnetic field amplification and neutron-star mergers. This is a topic that we've started to explore with our team in the last year, where we've taken some of the lessons that we've learned in modeling magnetic field amplification in core collapse supernova and apply these lessons in neutron-star mergers and think about how that could impact the observational signatures of these events, but also solve some basic physics lessons that we want to learn. Just generally, there's a lot of exciting stuff going on with extreme transient events, especially by advanced LIGO being in operation and detecting gravitational waves from binary black holes, but also from binary neutron-star mergers. There's been a lot of attention recently back on binaries. This, together with all the electromagnetic follow-up observations that are being taken by wide-field time-domain astronomy instruments that record supernova and transients in general, has really the potential to revolutionize the field of time-domain transient astrophysics and astronomy. So today I'm going to be showing results obtained with simulations for binary neutron-star mergers, and particularly how the remnant of binary neutron-star mergers and its interaction with its own magnetic field are important for both which remnant is left behind in these systems, but also what kind of observational signatures we can expect. Just to get everyone on the same page, and because not everyone here is like an astrophysicist, these systems are really unique astrophysical laboratories that allow us to probe conditions of matter that are at the very at its very extremes. So this involves testing matter at nuclear densities. So a neutron star typically has something like 10 to the 14 grams per cubic centimeter of density, or slightly higher in its center. There's heavy elements being synthesized. There are neutrinos that are coupled with the matter that are being released in the cooling of these events. These change the composition of material in the outflows. There's magnetic fields that are important for jets that are being emitted by these systems, so very, very intense beams of lights. And then also, since some of these objects are very, very compact and dense, it involves relativity, and specifically general relativity, where these objects, for example, for a neutron-star merger, are moving at a good fraction of the speed of light, maybe 50% or more of the speed of light in its final orbits before they plunge into each other. So these are really unique relativistic, but also nuclear astrophysics laboratory that allow us to probe conditions that we can't easily access in laboratories on Earth. They're important beyond just being bright and extreme events, since they emit gravitational waves, they emit neutrinos. They're important in how the galaxy evolves, how the galaxy is chemically enriched with heavy elements. But they're also the sites where heavy elements are nuclear synthesized in the first place. So like some of the gold and the platinum that we have here on Earth likely, for example, came from a neutron-star merger. And they're also where these objects are formed. For example, if you form a black hole as an outcome of a neutron-star merger, then you have your birthright of the compact object that you later on can study with LIGO as they may be coalesced within at the black hole. This field, and I've already mentioned this a little bit in the introduction, has really been revolutionized recently, or is being revolutionized right now with the advent of both advanced LIGO detecting gravitational waves rather routinely now for these events in its third observation run. And this combined with the electromagnetic follow-up abilities, where we can actually really pinpoint and look which kind of source in the electromagnetic band actually caused these gravitational waves. This allows us to collect much more information about the source and learn all these exciting insights. At the same time, and this is really important for a symposium like the Blue Water Symposium here, we have the computational tools and the computational hardware to actually study these systems in full physics, first principles simulations that allow us to study these in 3D, looking at all the instabilities, all the different physical effects that are happening at different scales, so that we can really use these models that we can build to interpret all the observational data that will allow us to fully interpret the wealth of observational data that we're collecting from these events. For neutron-star mergers in particular, what is important is the two components where we have seen both a GRB, which is basically a jetted emission of very energetic photons, gamma rays, but also radioactively powered light curves in the optical that are called the kilonova light curves, which you see here on the right. And the question is, while a lot of the basic models have checked out initially pretty well, so that the theoretical predictions built on simplified models have actually predicted these light curves, for example, beautifully well, there's still a lot of details that we need to figure out, like which remnant was left behind, for example, by GW 170817, which was the neutron-star merger detected about 2 years ago. And how does the remnant lifetime, for example, connect with what observational signature we get out of these systems, so that while we've been encouraged that we've understood some things about these systems, there's a lot more detailed work that needs to be done to fully interpret all the observational data that we have collected. What this ultimately will allow us that we can really learn in detail about these events by having the gravitational waves and an electromagnetic counterpart that we can fully interpret and pinpoint the source, look at which different sources look in different ways, and basically maximize the knowledge we can extract from the observational data that we are collecting. So this is really what we're trying to build a program for. This is not just my group that is doing that. There's a lot of different groups looking at different aspects of this problem, since it involves a lot of different scales, different physics. So like the part I'm going to show you today really focuses on the detailed evolution of the microphysical scale and the microphysical turbulence that is happening in these merger remnants just in the very first fractions of its lifetime. So I'm only going to be showing you simulations that cover a physical time of about 25 milliseconds. So this is extremely short. If you're thinking about the 2 seconds of delay, for example, that it took the gamma ray bursts from this system to actually emerge in the observation. So this will be a first kind of step in the puzzle where we need to then build onto these simulations and do longer and longer simulations where we relax maybe some of the physics inputs to then get a full picture of how this is important for the observational signatures. The real kind of goal ultimately for what my simulations will try to answer is what kind of engines do we form that could explain all these different observational signatures that we get out of these systems in the first place. So what are the detailed engines that can be formed? And then to take this a step further, how can we connect the engine back to the progenitor system? So saying you know your two neutron stars that are merging, you know their masses, you know which initial spins they had. Can we actually go as far as using these simulations, and this is really a kind of grander picture that I'm building here, 5 or 10 years down the line, can we predict from the inputs what the outputs will be? So really to actually make this connection between progenitor system to observations so that we don't have to always run 100 million service unit simulation on blue waters to figure out what one of these systems will look like in detail. Are there inputs that we can extract from these simulations? So this is really the goal, and that will need a lot of effort from the community in itself to actually solve this, as everyone contributes their little steps to solving this puzzle. Modeling these systems computationally is really a multi-physics, multi-scale challenge. So we need to handle the gas and plasma dynamics via magnetohydrodynamics. We need to handle gravity, and here we need to handle full dynamical general relativity to handle the merger and post-merger dynamics of these systems, a possible collapse to a black hole, extract gravitational waves. We also need nuclear neutrino physics to handle the equation of state of nuclear matter densities that are very extreme. We need to handle the interactions between the neutrinos and the matter, and we need to handle the nuclear reactions that are happening in these extreme environments. Ultimately, we also need a transport theory to model how neutrinos escape this system as they interact with matter, and how that impacts what the composition of the matter is. So really, this is all 4 fundamental forces fully coupled, meaning that it's difficult to solve all of this at kind of face value. So there need to be some approximations that we need to make, since right now no one can solve all of this in its full entity. So what I'm going to be focusing on is mainly, if this pointer is working, yes. We're focusing a lot of our effort on the magnetohydrodynamics and involving full dynamical general relativity. We also have the nuclear neutrino physics, but for the neutrino transport, we're making some approximations in the sense we're not solving the full Boltzmann equations. We're actually doing an approximation to that, since that is something that in the short time scale that we're trying to study, it's not yet the most important component of this system. But further than that, you also need to worry about modeling these systems in multi-dimensions, or ideally in 3D. There's rotation and instabilities that are not captured correctly if you don't do that. And so really what one needs is like cutting-edge numerical algorithms that we can put to use at like peta and exascale computers. So something like Blue Waters was instrumental in enabling some of these simulations to be done. The software code I'm using is part of an open source software collection of tools, which is called the Einstein Toolkit. This is a community code where you can go in and like download different components, tailor the application to your needs. So you can do black holes, you can do exploding stars, binary neutron-star mergers. So you can really kind of tailor this to your needs in general relativistic astrophysics applications. And I encourage you to go to einsteintoolkit.org, where a lot of people have put in a lot of work in writing good tutorials and having example input and parameter files that you can either set yourself up or set your students or postdocs up to use these use these tools to enable simulations that you're interested in modeling. In terms of the results, what we have done is like we've taken a neutron-star merger simulation done by a collaborator of mine, David Radice, where you see here, you see a volume rendering of the gas density. You see the two neutron stars in their final in-spiral surrounding in their final orbits before they plunge into each other, which happens just about now, where they start touching and being tightly deformed enough to form a single object. As this happens, some of the matter gets ejected into a torus surrounding the system, and then as the final object that's left behind spins down, it ultimately, in this configuration, forms a black hole in the center, which will happen in just about a few seconds, where you see the center collapse to a black hole, and then you have, as an outcome of this particular merger simulation, an individual black hole in the center that is spinning, surrounded by an accretion torus. And so this is a simulation done in purely hydrodynamics, as for magnetic field impact effects to be important in the in-spiral itself. These fields have to be pretty strong, and what we've set out is to take one of these configurations, but look at what different outcomes can be enabled by magnetic fields and the different characteristics of the system. So there can be either a stable neutron star, a prompt collapse to a black hole, which happens if the individual neutron stars had a very high mass initially. But what I've shown you in this simulation is that we get these intermediate phase where we have what we call a hypermassive neutron star. So this is a neutron star supported by its own differential rotation above its maximum mass that it could sustain if it weren't rotating. And then this eventually collapses to a black hole. And in this particular phase, differential rotation and angular momentum transport by magnetic fields can be very crucial in determining the lifetime of this final object, so that if we go in and model one of the particular instabilities, which is called the magnetorotation instability, which really couples individual fluid elements via magnetic field and is in that way able to transport angular momentum outwards, this can actually impact your merger lifetime, can also amplify magnetic fields. What is key is that this doesn't need strong magnetic fields to begin with present in the system. It does require a certain angular velocity gradient, which we generally have as an outcome of these mergers. And if we look at what the situation just after merger is, and on the left here you see the instability or the stability criterion. So anything in light blue and dark blue is regions that are unstable to perturbations in the magnetic field to this particular instability. So these would create turbulence and would ultimately transport angular momentum from the core of this rotating hypermassive neutron star. Looking at this, and this is just a rendering of cut through the XZ plane of the system, you're looking at a volume rendering of entropy. So what generally happens is that let me just play this again, you have a high entropy outflow along the rotation axis of this hypermassive neutron star until the point where it collapses. So this is now an actual MHD simulation. And if I go further than that, what we're looking at is like what the variation of involving different magnetic fields in this system can be for changing the lifetime and the evolution of this merger remnant. And this is initially just comparing a hydrodynamic simulation versus a magnetized simulation at low resolution, you see if we don't add a super strong magnetic field and we don't resolve the turbulence in the system, this is as a function of post-merger time, you don't really see much of a difference in the time where this collapses. What I'm plotting here is the maximum density as a function of time. As we're adding in different magnetic field strengths, you can see that even at the same resolution where you don't fully resolve the turbulence yet, you can actually push this object to collapse earlier by just having stronger magnetic fields that we choose as an initial condition that we imply here. This is mainly because the outflow in these scenarios carries away angular momentum more effectively as you have a stronger initial field that kind of collimates this outflow a little bit more. If we now go on and actually look at the same initial magnetic field but do it for different resolutions, you see that you can also change this lifetime of the remnant. And here it's like a little bit counterintuitive, and this is something that we're still analyzing right now, where we're actually seeing that the onset of turbulence delays the collapse time to a black hole, which is something which is puzzling us a little bit right now, and this is something that's in progress, so kind of state of the art of what's happening with these simulations, and this is something that we're analyzing right now. Ultimately, we want to use this to connect it back into simulations that actually allow us to connect these detailed properties of the engine and the small scale variations back into actual simulations that allow us to assess the timescales of a few seconds, where we can connect this to what does that do to the outflow properties. For example, which heavy elements are synthesized? Does that change if we include detailed magnetic field effects into these simulations? Just to summarize, so I've shown you that transient observations and gravitational wave and EM follow-up observations really kind of allow us to interpret observational data in an amount that we didn't have previously present. We need detailed, massively parallel 3D simulations as enabled by Blue Waters to interpret all these simulations and as in all these observations. And as a simple example of that, I've shown you that the magnetic fields in neutron-star mergers play a crucial role for how the merger remnant evolves, and that we ultimately want to use these simulations to connect back to observational data. And Blue Waters and high-performance computing in general is key to solving all these puzzles. Thank you for your attention.